Hello everybody. This video accompanies notebook 9 of the series of videos Exploratory Computing with Python. My name is Mark Bakker and I work at the Delft University of Technology. Today's topic is discrete random variables. We will carry out a few numerical experiments using random variables. For that we'll make use of the random sub-package of NumPy, and we'll start by importing that. We first import NumPy, import NumPy snp, and just because we don't want to have to type numpy.random every time, we type import numpy.random as rnd. So we can call all the functions in the numpy.random package by typing rnd dot and then an a. We will start by generating random integers, and for that the random package has a function called randint. So we type open parenthesis and then we type shift tab and we'll see what we have here. We have low and high, which is exclusive, which is common or default in Python, and then a size. So we can say we want to generate numbers from 1 to 3, including 3, so we have to add 1 to 3, and we want to have 10 numbers. If I hit now shift enter, I get 10 numbers randomly pick between 1, 2, and 3. And you see, if we run this again, we get a different random set. And we can run it again and again. Every single time you get a different set. Now sometimes it's useful to get the exact same set every single time. For example, when you're testing code or when a teaching assistant is trying to grade your work. For that, what you have to do is you have to set the seed. You have to tell the random number generator start from this seed. And to do that, you type in front of here rnd.seed and then a number. And that is your seed number. And now if I run this, I get a certain sequence. If I run this same cell again, I get the exact same sequence back. I hit shift enter, I get the exact same sequence back. If I pick a different seed, I get a different sequence. But every time I do this with the seed of 20, I get the same sequence back. Like I said, that's useful for testing. Normally, if you don't specify the seed, NumPy will generate the seed automatically in some clever way behind the scene. Let's carry out our first numerical experiment. Let's presume we have a bowl that contains 100 red balls, 100 blue balls, and 100 yellow balls. And we're going to draw at random from that bowl, and by every time we draw a ball, we write down what ball we have and we put it back. And rather than having a red ball and a blue ball and a yellow ball, I'll give them numbers. I'll say red is the number 1, blue is the number 2, and yellow is the number 3. And let's make this cell a markdown cell type, markdown. So this is the numbers we'll have. And we call them balls. We have balls, we draw random integers from 1 to 3, but we want to include 3, so we add 1 to the high value and we draw 10 balls. And we get a nice error message. Random is not defined, well, because it's called rnd.randin, right? It's from the rnd subpackage. And then if you print the balls, we get 2233, 2232. We don't get any number 1, so we don't get any red balls. But that happens to be the sequence we drew this time. Now, if we want to count how many blue balls we have, what we would do is we take this set of integers and we say, okay, balls is equal to number 2. That is the number of blue balls. And this gives back an array of the exact same length as balls, which is 10. And it will be true at the places where balls is equal to 2 and false wherever it is not. So if I run this, let's print balls. So we can check, right? We get a different sequence now, different seed, and we see the very first one is true because that is a blue ball, and then here at the end we have 2 trues. In number 7 and 8. That's also numbers 2. But if I want to know how many blue balls I have to count these. I'll say np.count non-zero, balls is equal to 2, And it tells us there are 3 blue balls in this sequence. Maybe I should just fix the seed so we know what we're working with, right? The rnd.seed number is, say, number 10, which has a bunch of blue balls. In this case, 6. 1, 2, 3, 4, 5, 6. So we can count them with the np.count0. In fact, we can also, from this numerical experiment, determine what the probability for a blue ball is. And that the probability we determined from the experiment of drawing 10 balls. We can calculate the probability of blue. It is equal to what we just had, np.count0. Here we go. And we divide it by the number of balls, which is 10. And we print probability of blue is equal to prop blue. And we get that the probability of a blue ball is 0.6. And we know that's not true, right? Because we have 100 red balls, 100 blue balls, 100 yellow balls. So the probability of a blue ball is 1 over 3, 0.3333. But based on this one experiment, it's 0.6. So let's get rid of that seed here and let NumPy generate its own seed so we get a different sequence of random numbers. In this case, our experiment would tell us that the probability of blue balls is 0.2. If we run it again, it's again 0.2. That's lucky. Now it's 0.5, right? So apparently, if you do an experiment and you just draw 10 balls, you don't get a very good accurate estimate of the probability of that ball. What if you do 100 experiments? So let's introduce a new variable called n, which is the number of balls we're going to draw, and we make it 100. So now here we draw random integers and we draw n of them, which is 100. And when we calculate the probability, we divide through by that n. Do we still want to print all the blue balls to the screen? I don't think so. Let's put a marker in front of that, or a hash. And wow! With 100 balls, we get exactly 0.33. Now that's just luck. If we do this again, we get 0.34, we get 0.32, 0.37 even. So 100 gives a much better estimate of what the probability of a blue ball is than if you do it with 10. And that makes sense, I hope. If you do the experiment 1,000 times, so 1,000 times we draw a ball with replacement, we get an even more accurate. We get now 3 digits, right? But you need to do it maybe 10,000 times to get more accurate results, right? Every time we are pretty close to 0.333. That's one way of doing the experiment. Another way of doing that is say, all right, we don't just draw random integers, but we create an array that has 100 red balls, 100 blue balls, and 100 yellow balls. So it's an array of length 100, and it has 101 values, 102 values, and 103 values. So let's call that array bowl. Bowl is np.zeros, and we have 300 values, and the first 100 values are the number 1. We make this, by the way, we want to make this an array of integers, because we want to have whole numbers. From number 100 to number 200, we give it the value 2, those are the blue balls. And from number 200 to number 300, we give it the value 3, which is the yellow balls. We can now draw n balls from this bowl with the function called choice. So we store them in the variable called balls. Balls is rnd.choice. And if we hit Shift Tab, it tells us it needs an array that we're going to draw from, and our array is called bowl and then a size. So we're going to draw from the bowl and with a size n. And then if you hit Shift Tab again, it will tell us the rest. We can even tell it whether we want to replace that ball, replace equals true, which is the default, or we can say don't replace it. Then we make replace equals false, and then every time we take one out of the bowl, there will be one less of that ball. Once we've drawn those balls, we can calculate again the probability of a blue ball, just like we did before. And we can run it. So I hit Shift Enter, and we get our probability is 0.2, or 0.5, or 0.6. And we can again increase the number of balls we draw from this ball to 100, 0.31, 0.3. But now we can, we do this with replacement equals true, but we can also do it with replacement equals false. So we go to this choice function and we say replace is equal to false. And now we draw 100 balls, but every time we don't put it back. And we get a different probability out of that. And this one, oh, this stays pretty constant. Oh, there we go. I hit Shift Enter every time, right? If you see the screen flicker, I do a new experiment. Now, if I would do 1,000, I think you cannot do that because there's only 300 balls in the ball. So if I ask it to draw 1,000, it should throw an error message, and it does. Does it give it? Cannot take a larger sample than population when replace is equal to false. That's actually a pretty good error message, but we can do 100. Finally, this choice method allows us to do experiments where not every outcome has the same probability. In this case, we have 100 red balls, 100 blue balls, and 100 yellow balls. But what if we have 100 red, 50 blue, and 150 yellow? We could very well have that, right? So we go here, we change the cell to the cell type markdown. So this is not code we want to run. We can do the same thing. We copy this right down. We have a bowl, again with 300 balls in this case, right? It still adds up to 300 for the choice we made. The first 100 balls have the number 1, which we call red. The next 50, so from 100 to 150, are the number 2, which is the blue ball. And from 150 to 300, we have the number 3. We can still draw 100 balls out of that. We can still count all the blue balls, which means that the value is equal to 2. We can, once we've counted them, we can draw them, divide them by n to get the probability of a blue ball. And the probability is now, well, there's 50 blue balls in a bowl of 300, so it should be 1 over 6. And let's put the replacement back to true, so we erase in this case the keyword. We can run this, and we get indeed something that's very close to 0.16. But not as accurate, right? If you do this 100 times, but now we can do it 1,000 times because we have, or maybe even 10,000 times, because we don't have replacement. We don't replace, we put the ball back, replacement is true. And now you see we get nicely about 1 over 6 every time I hit Shift Enter. That's all I had for you today. I hope to see you next time.